Okay, so what is the agenda that I have got? I've got planning to cover the powertrain and powertrain components overview, design calculations, and simulation. So this is all what I would like to cover today. Okay. So what you all said is absolutely right. So this at least uh, I'm part of SAE India Southern section activities, volunteering for different activities, competitions like this electric four-wheeler design competition is something we call as project-based learning. So where you are assigned a task to develop a vehicle that's going to function. It's a working prototype that you're going to develop. So you're actually going to experience all the fundamentals. Like someone said, Rishi, I think he mentioned. So you're going to brush up all the fundamentals. Now you're going to experience it. What if something goes wrong? Or maybe if one of the parameter you have compromised, how was it going to have a effect on your vehicle? So you're going to gain this by working on a model. So it's going to give a lot of learning. And today's session, that what I'm doing, I'm also going to learn from you guys. I'm going to tell you what I know from the powertrain calculations and standpoint. But the more we interact, I also would like to learn from you guys. That's the whole idea. So it's not a session, or maybe it's not that I'm going to present all the slides and go on. Rather, it has to be interactive so that it will be benefit for both of us, and we can go slightly deeper on the topics that you're interested. And for the topics which you have questions, we can dig deeper, we can take some examples and discuss. So that's the whole idea. Okay. All right, now let's start. So what is a powertrain? So it's a very basic terminology, but just want to be sure it's not, I mean, it's better to learn. It's even it is late, it's better to learn now, not that learning ever. Okay, so what is a powertrain? It can be anything. Since it is powertrain, we have not specified an automotive, but yeah, it can be any mechanism by which we generate energy, we generate the power, we are transmitting it to the environment. May it be road, surrounding air, water, or whatever it may be. And for us, as you all know, I mean, this is now maybe, yeah, it's familiar. You all are well aware that the key components of the electric vehicle powertrain are the battery, motor, and the drivetrain. Okay, what are the key components? Yeah, we just discussed that: the motor, the battery pack, and the controller. Of course, I mean, at least these, for sure now the transmission, all these integrated. So an axle, a battery pack, and the controller. These are now the key components, or at least components that we are going to concentrate today for this session. Okay, so um, just giving you some idea. So, what can be the range of voltage? I mean, apart from the competition, let's also dive, or maybe go little bit out of the competition here, and just understand what is there in the market. Do you know what is the range of voltage, a battery voltage that is usually present in the vehicles that are in the market? When talking about the battery, what do you think is the rated voltage of a battery present in a maybe an EV, an auto rickshaw, and a electric two-wheeler? So it depends on the application. For an electric wheel two-wheeler, we may probably have around 48 volt system. I mean, it can be probable only, we can say, because there can be a startup which can work to develop maybe 72, use a 72 volt system, or even they can go up to 400 volt system. So there is no restriction. For now, that's what is ideally present is, let's say we have battery systems ranging from 48 volt, 72, 96, and then the widely used for automotive are 400 volt for pass cars, also some light commercial vehicles. Now there is still research going on to have systems which are up to 800 volt system, 800 volt power systems, and even above that. Kilowatt systems is also, kilovolt system is also in development. If I ask you, there is one key advantage of increasing the, what happens if we increase the voltage? I mean, voltage, when the voltage increases, I mean, your power is voltage times current. So when the voltage increases, yeah, your current passing through the wires can be smaller, which means which has a direct impact on the wires that you are going to use. The more the voltage, your wires can be thinner, which would end up reducing your weight of the vehicle. There are a lot of high voltage, or maybe when you take the complete vehicle, your high voltage routing is also a major component of weight addition. Okay, and what is the safest voltage in DC for a human being? 60 volt DC. Okay, 60 volt
60.
DC is the safest DC voltage. So in any case, like if your battery is below 60 volt, then you'll not feel a shock. Your body can still, or your body will not be harmed by that. So again stating this point why I raised this. So take a case of a vehicle with 400-volt battery. If there is something critical happening, or if there is an isolation failure, or if there is a open wire, now now what the system has to do, your controller, it has to detect this situations, and it has to reduce the voltage present in the high voltage bus, or a high voltage bus to be less than 60 volts, not the battery voltage. If it is a 400-volt battery, the controllers are not expected to reduce that voltage of the battery, but it is just the place. I mean, your storage can have it, but the distribution should be reduced below 60 volt in a fraction of seconds for the protection. So these are some quick thoughts around, or general points about batteries, battery safety, or maybe voltage ranges used, and so on. Okay. Okay. Now, controllers. What are the controllers present in an electric vehicle? Since you are going to build a maybe electric four-wheeler, what do you think are the controllers that you plan to use in your vehicle? At least I expect three main controllers. Hope you are aware. So I would like to understand what do you think. You may have your battery management system. Do you agree? And you'll have also a motor controller. Am I right? While developing a vehicle, not just here, even in any company, what we do as the first thing is that we develop the vehicle architecture. When I say the architecture, maybe the electrical electronic architecture, where you'll have your battery power source, and then you'll have your DC converters like your friend mentioned, but and then a battery management system, a motor controller, and also for your case, your motor controller can act, or you can buy a get a combined motor controller plus BMS plus your vehicle controller. But many cases, for we'll also have a separate electric vehicle control unit, something like that. So those would also be some of the power electronics that is present in a vehicle. And apart from that, the cars that runs on the road, that needs also, that should also do a charging by connecting to AC power. So it also has an onboard charger. So these are some of the key components of, I mean, when I say the power electronic components present in a vehicle. And then motors, we'll see the different types of motors today. Let's first look up about the batteries. So maybe what I have is a presentation which we used to, I mean, do it for our day training. But now since we're doing it in a short time, I'll be skipping some parts of it. And since some of these you already know, so I'll skip some of this. So I got a YouTube learning video on working principle of a lithium-ion battery. I'm going to skip this, but I assume that you all are somehow familiar about the working principle of the lithium ion battery. Okay, but I'll just touch base on touch base on the battery pack. I mean the chemistries. So as you know, lithium ion chemistry is the one which has the highest specific energy and the specific power. So So, I mean, when we look at the trade-off between all these chemistries, say lead acid, I mean, nickel cadmium, nickel, I mean, lithium polymer, lithium ion is the one which has the specific energy of close to 180. This is a slightly older chart. When you look today, the process has been improved. The cost of lithium ion has also come down. So, yeah, so with the lithium ion, that's why lithium ion chemistry is widely used for your automotive batteries. And when we look at the volumetric energy density and the specific energy density, here is a plot where lithium ion batteries are in the range of say 150 to 220 whatever per kg. And you know the packaging constraints and the weight restrictions that we have on a vehicle. Say you have a battery pack of, let's say 10 kilogram, and when it is at maybe for a two wheeler, or maybe let's take for an electric vehicle, it can be around 200 300 kilograms. Now at 100% charge, your 300 kilogram is going to store energy that can be used for driving close to say 200 kilometers. Now at the 10% of charge, your 300 kilograms of vehicle is going to take you to maybe say 20 kilometers. So that's why it's very critical, the energy density, that energy density is very critical. And we that's why every aspect, I don't know if you follow these news recent days, compared to an internal combustion engine versus an electric vehicle, the companies, automotive companies, are looking to reduce the weight as much as possible everywhere. So you could also have noted all the electric two-wheelers that we have on the market. Your old Activas, all these used to have, or scooters used to have grills at the front, at the back, to protect your chassis. Now these days, if you take a closer look, all your vehicles, electric two-wheelers, which you buy from the companies which are offering electric two-wheelers, mostly there are aspects. I mean, they have considered the weight reduction to the maximum extent. So you could see, I mean, these are smaller things which you can witness. Likewise, the volumetric density, packaging of your batteries. Now, mostly you could have noticed that we have the batteries packaged in the platform of the vehicle. So volume and weight plays a major role. Again, lithium. I mean, this is chart just to give you a glimpse on what are the chemistries that are available and why we are choosing lithium-ion battery. I hope many of you are already aware, but just this is to brush up for those who are looking at for the first time. Okay, cell form factor. Uh, these are the typical form factors that are available: a cylindrical cell, a prismatic, and a pouch cell. Now, the main difference is that you'll for the cylindrical cell, you will have your anode, cathode, and the separator rolled to form the cylinder. Whereas for your prismatic, you will have a solid case. That's the only difference between the cylindrical and a pouch cell, where you will have maybe a foil, maybe a thick aluminum foil to cover it. So these are the form factors, but there are also there are also other types which are derived from this form factors. A blade battery, for example, with the length of the battery would be longer. That's why they call it blade battery, which is derived out of this prismatic configuration, or this prismatic form factors. So the the most commonly used chemistries of lithium ion batteries are maybe just mentioned here to give you a quick glimpse as well. So in the recent days, the most maybe when we look at the trade-off, the NMC battery chemistry is most widely preferred, since it trades off well with all the factors. I also have got a table to show you that lithium nickel NMC. NMC stands for nickel manganese cobalt oxide, And likewise, you also have LCO, lithium cobalt oxide batteries, LFP, that's lithium iron phosphate battery, and then LTO, lithium titanate oxide batteries. So these are yeah, LMO as well. So these are the five different types of lithium ion chemistries that is widely used for the automotive grade application. Here is a comparison of these chemistries. I'm rushing through the slides since this is just to brush up, where powertrain calculation and the simulation is going to be our core topic that we want to discuss today. So you see a quick look. Let's take specific energy as one example. So NMC has specific energy of around 150 to 220 watt hour per kilogram, which is better compared to all other chemistries. Likewise, the energy density as well. So the two critical factors that we spoke about, the volume and the weight. So NMC does very well on that. And yeah, but when you look at the performance, when you look at the performance of this batteries, it has a shorter charge rate, C rate. You may have known C rate, the rate at which you can draw out energy from your battery. So NMC has a C rate okay compared to, let's say, LTO. LTO is a chemistry which can sustain a very fast charging and discharging rates, and it can sustain also thermal runaways, or maybe it can also operate on very high, I mean, environments which show heat. But the compromise would be like the cost of LTOs are higher compared to NMC. So this is to give you an idea. How also this also is common. How this cells are, or why is the cell called 18650? Because of the fact that the diameter of the cell is 18.40 mm, and then the length of the cell is 65, and since the form factor is a circle, that's why this is called 18650. There are other, I mean, similarly, when you take a uh, when you take the cylindrical cell, you also have maybe the other form, I mean, dimensions as well. uh, I heard Tesla recently also have got somewhere around 44, and so on. I'm not sure, but okay. Okay, now since we spoke about battery, one thing I would like to say, while you source your battery pack, you should get the data sheet, battery data sheet, or before you source, when you are doing a comparison, try to get the data sheet, battery data sheet. May not be, I mean, the supplier that you are approaching may not be as standard as Panasonic, LG, or other companies which is providing the batteries, but try to get the data sheet first, do an analysis, look at the parameters present in the data sheet, compare between the cells. This is again going to be an exercise for you while you choose your battery pack. You may get to know a couple of parameters: the charging discharging rates, range the range at which your batteries, the temperature, it's not going to be constant. So the temperature while charging the battery has to be, or this battery is compatible to be charged between 0 to 45 degrees. So when you have a sub-zero temperature, you have to find, I mean, when you develop a vehicle, that's when you apply engineering to get to a situation where you have to first condition your battery pack to reach, to have your cells between this, the temperature that is provided by the supplier. Likewise for discharging as well. So you cannot exceed this limit. But meantime, that's how the thermal management system has to be defined. But the whole idea here for this slide is to tell you that get the battery data sheet, gather the information, analyze it, and then choose a battery pack rather than buying off the shelf, just looking at the cost. But cost plays a major role, but also do a comparison and a thorough analysis. before you source your battery pack. Probably the battery data sheet will also have the battery performance and the characteristics data. So do also an analysis on that before you source it. So motor also got a short animation on working principle of a BLDC motor, but I'm also going to uh, skip that. But here there are different types of motors. Like you we can have a DC motor and an AC motor. Now choosing of uh, uh, the motor again is an activity where you can form teams, subgroups in an automotive. Development. The teams are split like maybe a team would be responsible for energy management system, a team will be responsible for torque management, a team will be responsible for chassis development, integration, testing. So likewise, you can take up each of these subsystems, divide your vehicle as a system into different subsystems, and you put efforts to do a detailed analysis before you proceed. Now, one quick table on the comparison between an AC motor and a DC motor. You have an induction motor synchronous, whereas when you look at DC motors, you can have a brush or a brushless DC motor. The yeah, speed, your speed of the motor is directly, controlled by the PWM signal that you are going to send. Whereas for the DC motor, you have, your controller. This is what your controller is going to do when your controller gets the throttle input, the PWM signal. If it is an AC motor, motor controller is going to vary the PWM frequency. For the DC motor, the armature winding current is modified uh, to to provide you the sufficient, to provide the torque demand that is sent through the throttle. Now let's come into the core topic, the powertrain design and the powertrain calculation. So, what are the inputs that we have? First of all, uh, uh, why should we do this powertrain design calculation? Please unmute and respond. Why should we do a powertrain calculation, or why are we doing this powertrain calculation? Go to a shop, you go to a supermarket, you will have a lot of options. You're going to buy juice now, or you are going to buy vegetables. Maybe vegetable is not a good option, but let's check juices. So you have a lot of options, right? When you're going to buy a product, you have different options. There can be ranges. So likewise, if you want to, what we saw that we have core components, or at least for this discussion today, we said we're going to concentrate on battery, we are going to concentrate on motor, and we're going to concentrate on the controller. Now, how should I choose? There are motors that are rated to 1 kilowatt, uh, and there are also motors at 2 kilowatt, 2.5 kilowatt, 5 kilowatt, and it goes on. Likewise, there are batteries, uh, uh, maybe at 48 volt, and then 20 ampere hour, 24 ampere hour, uh, and it goes on. It goes on. Likewise, controller. Maybe controller is a different story, but now let's talk about these two. So there are different motors. When we look at the power rating, the torque which it is providing, and so on, there are also different batteries of different capacities. How should I choose this? How do I know that I should choose a motor of say 2 kilowatt, or I should choose a battery that should be providing an energy of at least, energy of say 24 ampere hour, a capacity of 24 ampere hour, or 40 ampere hour, whatever. How do I know that? How should I choose that? Okay, cool. Okay, any other thoughts? So we said that I have a need. I'm developing a vehicle. I know what this vehicle is going to do. Someone who may develop a golf cart, someone who's going to develop a F1 vehicle, there's a difference, right? So now I have a need that I have a situation that I'm going to develop a vehicle for this purpose. I know this purpose. Now for that, I have to choose a component which fits this application. So that's how we do that. This is more a definition. Now, when we want to do this actually for selecting a motor or selecting a battery, how do we do that? That's what we are going to look at today, slightly in detail. So what are the inputs? I have listed down that these are the inputs that are available with us, and these are the outputs that we wanted to take out from this design calculation that we are going to do today. So uh, let's talk about this gross vehicle weight. If you ask me, we really don't want to go into simulations as well, but you're going to build your chassis, then you're going to, or maybe you'll also be feeding, you can feed the parameters, like say what is the material that you are choosing for your chassis, and then what is the material that you are going to choose for your cover body of your vehicle. And then for components like a battery pack, you can get a round off number. Say if you want to have a 2 kilowatt or maybe 1 kilowatt battery, it will be around 3 kilograms or whatever. So you can get a round of value for that, also for the motors. So these are commonly available, but for the space chassis, that's going to be customized for your application. Like you all said, you can have your CAD model, which can estimate you based on, I mean, you should, I mean, it's not that CAD model is going to directly give you the data, but you should also fine tune it by specifying the material properties. Then you can estimate the gross vehicle weight. Gross vehicle weight. Okay. So this I think we are okay with this. Do you all agree? Any questions that gross vehicle weight is an input that we need? Vehicle maximum speed, yes, this is a boundary condition that is already provided. The vehicle should be designed to not to exceed, I think it's 25 or 35 kilometer per hour, but yeah, after the rule book, but this is the max speed that is specified. Vehicle acceleration, you have a speed, I think now you can easily calculate the acceleration. uh, so, and then gradability also, I think there is a guideline provided for the gradability, but I'm not sure, but I want to ask you, how is this gradability parameter chosen for your as a vehicle input? So do you all drive vehicle? Do you drive a two wheeler on the road? Okay. Have you noticed that almost all the bridges on the highway, on any road, the gradient would be same? Do you agree? That is on the road. I'm not saying any private slopes, but when you take any government built roads, the grade on the bridges are going to be the same. Is it correct? Good. How do they get that? This is a parameter that is fixed by the road. Road development authorities or Indian road standards. So when you are building a vehicle, and if we are planning to use this vehicle to be driven on the road, not for any special application inside any campus or something. Now, if it is built to be driven on the road, then you have this parameter as an input. You know that gradability of as per the standard is around 13 to 15%. It can be between 13 to 15% grade, which comes up between anywhere between 7 to 9 degrees grade. So we, and this is also an input. Now the tire size, probably the session, the workshop that we had, our expert should have explained you how do we choose the tire, and what do we mean by tire size? How how we read that tire, maybe the radius that is printed on the tire. How do we read that? It is diameter. Yeah. And the outputs that we are going to take out today are the tractive force, the torque, peak power. We are going to select the motor. We are going to select the battery. So this is all we wanted to do today. Okay. So now I'm uh, okay, a free body diagram of the vehicle. So quite familiar for all of us. Your weight acts towards the ground, and you have a normal force, and then you have the thrust and the friction force. And when you are on a grade, you also have your forces due to the gradient force and so on. So what are the forces that we should consider uh, for calculating the power and the force required to propel the vehicle? So we aerodynamic drag force. Are you all familiar with this aerodynamic drag force? Okay, we will see that. So aerodynamic drag force, the rolling resistance because of your tires, the gradient resistance or the hill climbing force, and the acceleration force. So these are the forces that should be overcome. These are, I would call it as, all these are the resistance that acts, which so a vehicle that has to propel has to overcome all these resistance before before uh, before the next before moving it further. So what can be your total tractive force? When we look at the total tractive force, these are all the resistances. But when I want my vehicle to move, what is one additional force that we have? Come on, guys. So the total tractive force is sum of all these resistance. We saw the rolling, or we just discussed. Maybe the total tractive force would be the resistance. You have to overcome the resistance. You have to overcome the aerodynamic drag. You have to overcome the hill climbing resistance, and then to propel your vehicle forward, you'll need a lateral acceleration or linear acceleration, and then angular acceleration. Since we have rotating components in the vehicle, so we also have angular acceleration. So summing up all these would give us the total tractive force. Why uh, why do we now why are we calculating this total tractive force? What are we going to do with this total tractive force? We are going to look at individual each of these forces, but then before we go into all these forces, and we look at the formula for calculating that, let's quickly talk what is our objective. What am I going to do with the total tractive force?
We're going to find the power.
You said it, yeah. So like we saw in the previous slide, force with the force we are going to find out what is the torque required, and with the torque we are going to find out what is the power that I need to propel my vehicle, and with the power we are going to look at uh, what should be my power rating of a motor. Now I'm going we are going to choose a motor. We're going to choose a motor by doing a physical hand calculation of all these forces that we should overcome. What should be my torque? What should be the power that I need? And with that, we know the motor that has to provide x newton meter torque. Uh, Now, and then a power of say x kilowatt, 1 kilowatt, 2 kilowatt, whatever. And then with that, we are going to choose a energy storage device, a battery pack, which should provide x kilowatt of energy to the motor for it to propel the vehicle. And this is what we are going to do today. And all these are quite familiar for all of you. We are learning it from our schools, but we'll brush it up now. We are going to look at, or maybe the whole loop from selection of your or maybe drilling down from calculating the force to selection of motor and a battery, probably we that's not an application oriented exercise that we may have did it, but we'll see today. So what are the maybe let's look at I mean, let's start with all these forces. Aerodynamic force, what are the major contributors of an aerodynamic force?
Air density, speed of the vehicle.
Oh yeah, you're right. Speed of the vehicle is a very critical parameter for the aerodynamic drag for calculation. Okay, air density is pretty much going to be the constant. Probably when we are driving to a hill station, it's going to be slightly different. But considering at least our case, we are going to operate it normally. So probably the density of air would be a constant. What is other one important factor from your vehicle perspective that is going to affect your all right. Okay, All right. The next one is the rolling resistance force calculation. So it's the coefficient of rolling resistance times your mass and acceleration of the vehicle, and of course your slope also plays a or is a contributor for your resistance force calculation. Again, for all these parameters, don't just I would kindly suggest you not to uh, search in just web pages to get get the data, rolling resistance data. Rather, try to understand or try to find what is the standard that I should refer to get the rolling resistance data or coefficient of rolling resistance data. And then accordingly you can spend time to find out what is the rolling distance. This way you are also, the point that we wanted to state is that there are standards for all these. We should ideally not assume any information. We should either look at the standard, we should look at the standard and then take the data. So this is for the rolling resistance force. And then gradient force. Yes, when you have a grade, uh, it's like you resolve the forces. It's mass times the acceleration and the sign of slope that we have. And as I said, how do you calculate when you have a to convert from 14% or maybe 13 to 15% grade to degrees, we usually use tan inverse. As you know, tan inverse of 14 by 100 would be like I said, the grades usually are between 7 to 9 degrees to my best information. But also this, for this you can also look at the standards to get the correct to verify if this information is right, and you can use that data for your calculation. And with this you will have your total resistance. You'll have the total resistance. We have just discussed about the aerodynamic drag force, the rolling resistance force, and the gradient or the hill climbing force required if you want to climb a grade. So these are all the resistance forces that we should overcome. Now to further propel the vehicle, we need lateral acceleration, linear acceleration. So and the angular acceleration, which is caused by the rotating members present in your vehicle. And we all know that from the Newton's third law, force is equal to mass into acceleration. So this would give us the linear acceleration of the vehicle. Okay, now angular acceleration. This is one of the important or interesting topic to me at least. So what are the components that are going to cause angular acceleration in a vehicle? We have motors. Yeah, we have motors or motor. Maybe if you're going to use a single motor, but there are vehicles with multiple motor is a contributor of angular acceleration. And then we have the transmission systems, which also uh, causes the angular acceleration. Now the formula for calculating, it's also the same. The force, your force is always or a torque. We look at torque. Torque is force times since it is actual angular acceleration, force times the radius. Uh, so when you resolve this, we get to this formula where force is equal to moment of inertia, your square of gear ratio, and efficiency of your system, and then square of the radius times acceleration. But there are many times, in my experience with the OEM, uh, we may not be able to get all the data, like a moment of inertia of your motor. The technical or the specification of the or the motor specification will not give us this information. So for that, how do we manage this? We can do a simple approximation. So what do we do? angular acceleration, when you compare angular acceleration versus your lateral or the linear acceleration, angular acceleration probably is usually around 5% of your lateral acceleration or the linear acceleration. So for that reason, and maybe a small approximation is done, whereas your you are increasing your mass of the vehicle by 5%, and you're now getting to a effective mass calculation where you are increasing the mass to compensate this force due to your angular acceleration. And this is an assumption, and this in itself is a maybe a detailed topic to discuss, but to give you a glimpse, this is how we can also approximate to consider the effects of angular acceleration also to the calculation. And when we sum up all these, we get the total attractive force with all the parameters that we saw, or we know the total force. And with the force, okay, I mean, ignore this numbers, we were using it for a different calculation, but yeah, we have the total force. With that, now when we wanted to calculate the power, power is velocity times force, or force times velocity. With that, we know we can calculate the total power. I mean, at least for this case, maybe we did some calculation, and maybe the total power that is required comes up around 3 kilowatt based on all the assumptions that we had, vehicle weight considered, and so on. So this is what we had. Now a question. I mean, the power that we calculated, the force that we calculated, which we used to calculate the power, do we need for this assumptions whatever had, say, I mean, ignore these numbers, but say I have calculated and I found out I need a 2.7 kilowatt of power based on the force that we estimated. Do we need the same power throughout the driving? Say I'm going to drive an hour for 30 kilometers or whatever. Do I need a continuously 3 kilowatt or 2.5 kilowatt, whatever I calculated?
I think so, sir. This for a pickup. This power is required to change the vehicle from static to a dynamic state. So I think when it start to accelerate, the power consumption will reduce. But also it depends on the road conditions.
You're right. Okay. Yeah. So you're right. This is not going to be the power that we need throughout. So we were overcoming inertia. We had the inertia force initially. Now we overcome that, and then we kept the vehicle propelling. So now when you are already at a constant acceleration or constant velocity, your acceleration is zero. F is equal to ma. So we may not need a power whatever we are going to calculate continuously. So this is going to be a peak probably if you are considering grade as well, and the power, the total power we are going to calculate is around the peak power. I have a slide on the drive cycle. Maybe we'll come to that in the upcoming slide. But now, yeah. So total power. I mean, when yes, what you said is right. The power is required only when the vehicle is accelerating. When you're not accelerating, your acceleration force, the force due to the linear acceleration will get cancelled out. You'll be in inertia. Okay, and now, okay, now we wanted to we have now found out what is the torque that I need, what is the power, what is the power that I need. Now, how do we select a motor? So these are some of the critical parameters, or at least the parameters that we should really look at for selecting the motor. So where do we get all these data? Again, a data sheet. A data sheet of your motor manufacturer should provide this data: a nominal voltage, a maximum voltage, which can be provided for this motor, nominal current, or the continuous current and the peak current. What is the difference between these two? A continuous current and a peak current. Any idea? Any guesses? What's the difference between the continuous current and a peak current? So usually the tech specifications would be in such a way that the motor may demand a continuous current of X ampere continuously for its operation, whereas peak current is like when you're suddenly accelerating, uh, when there is a sudden torque demand, then your motor may need up to maybe let's say two times the uh, uh, two times the current, but it is going to be for few seconds, or even sometimes it is fraction of seconds. So that's this these are the information provided. How critical is this information now? These informations like a nominal voltage, a maximum voltage, nominal current, continuous current, peak current, this should be in line with, or this should be considered while you choose a battery pack. Your battery pack is going to be your energy source that should be providing the energy to the motor. So this should be eh, this should correlate with what the battery that you're going to choose. That's why these parameters are important to be in line with the energy storage device as well. Now the rated power, the continuous power, this is the power that we want the motor to provide all the time. Peak power is when, in a rare case, when you want to climb a steep grade, a special case, or when you have a load, a maximum load, or you have designed a vehicle for a GW of X kilogram. Now you have the whole weight of the vehicle. Now when you have all the resistance forces and you want to do a linear acceleration, and that's when you need the peak power and the peak torque, and the motor maximum RPM and the efficiency. These are the parameters that would be part of the data sheet. Again, let's get 2 3 data sheets, do a comparison, and then we can choose the motor. And yeah, the power rating of the motor, I mean 2 pi nt by 60. That's how we correlate with the power rating of what is the power that is demanded, and what the motor can provide. With the data from the data sheet, we can calculate and we can see if this is in line. And the same has to go through for your controller selection. So the electronic component, your motor controller should also have compatibility to accept a nominal voltage and maximum voltage. Most of the cases, the motor and motor controller would be from the when provided by as a pack. But uh, if in case it is bought out separately, or you're even when you're buying it, you can do this comparison of nominal voltage, maximum voltage, nominal current, and the peak current. And similarly, the same has to be referred to your battery pack as well. Okay. Yeah. Now, okay, this is the energy calculation. How much energy do I need? Uh, okay. Let me do this with this battery pack. Okay. So here, ignore the numbers, but what I have done here is to compare, or maybe doing a conversion from joules to kilowatt hour. So how do we and let's say we are choosing a motor of power, let's say 4 kilowatt, and we have what is the total amount of energy that is required is calculated with this formula. Sorry, this is the calculation for the battery. I got slightly confused. Okay, so battery pack calculation. So how do I know that I should choose a 1 kilowatt battery or 2, 3, 4 kilowatt batteries? How do we select that? Uh, in principle, this is going to be the range that you want to cover. One, you should be having the capability to support your motor to provide the energy, and consider the case when you want to when you want to drive. Let's say you have an application where you wanted to drive 30 kilometers, 40 kilometers, then this is also a point that we consider for the battery pack calculation, or how we choose our battery. So we know, we know that the electrical energy would be the voltage times ampere hour. So uh, a cell, so to measure the voltage, what do we do? Voltage is measuring the potential difference, right? So we'll have a sense here, and then this is how we measure the uh, cell's potential difference. When you have cells connected in series, what happens? So you have more than one cell, so you're going to measure the potential difference between the this point, say a positive terminal here and the negative terminal, when you have, let's say, more than a cell connected in series. So it's going to be the potential difference. So cells in series would increase, I mean, would add up the voltage. So let's say you have let's say a 3.2 volt nominal voltage cell, and you have 10 cells in series, you will have 32 volt. Likewise, when you have parallel configuration, that's when your voltage remains the constant. I mean, voltage would be the same as all the cells, and then your current or the capacity would be increases. So now, for us, if I want to have 1 kilowatt hour battery, and if I mean, here, as per this regular, I mean, as per the guideline here for this competition, since 48 volt is fixed, now if I want to calculate what should be my ampere hour, it can be like, say, if I'm going to use 1 kilowatt battery, I can have an ampere hour of around 21 ampere hour. So we now go back to look at what is available in the market. Many times it can be like, say, 21, 24, and it differs between different suppliers. But do you know that the usable energy of a battery pack is just 80%, or even lesser than that? Do you know that? Why? Always, maybe even in your mobile phones, for any devices that has batteries. So we have, you are probably familiar with this terminology, SOC, and we also have DOD, depth of discharge, which are quite similar, both of these terminologies, SOC and depth of discharge. Now, batteries should not be overcharged and discharged below certain limit. Batteries or the cells has some uh, conditions, or cells has a inherent property that it when we want the life of the battery or the cell to be improved, it should not be charged to its fullest, and it should not be discharged to the maximum extent. So there is always a buffer. So usually the buffer on the top is around 5%, and the buffer at the bottom is around 10%, or 15%. Yeah, meaning you are, when you are charging your battery, you are always going to charge only till 95% of your actual SOC of your battery. And when you are discharging it, when your mobile phone, or when your EV battery shows you're at 0% charge, you are actually, your battery or your cell is having at least 15% of SOC. So this is a protection limit that is kept. So that's why usable energy many a times is anywhere between 80 to 85% of the battery's actual capacity. So if you also consider that, now you're, I mean, to have 1 kilowatt of usable energy, you may probably need 48 volt and 24 ampere hour battery pack, which would give you 1 kilowatt of usable energy. And now, I mean, this is not a hard number, 24 ampere hour. This absolutely should be based on your application and your need. Okay. Now how do we do this? How do I know that how many cells should I connect in series and how many cells should I connect in parallel? This is purely based on the cell that you're going to choose, or the from the back pack. So this is your requirement. Now also go back, look at what when you look at your text specifications from the supplier, you can have cells of different voltages. Now based on that, you will also have a cell of different capacity rating. Now with this information, you have to connect, I mean, you can calculate to know that how many cells should be connected in series and parallel to get you the needed configuration. So one, I mean, this is for you to do the calculation, but maybe at least for this competition, we don't recommend you to buy cells and assembling it on your own. We suggest you to buy the pack, assembled pack with the hard case. But one thing I would like to stress here is it is not about just buying the battery pack. Rather, you should know why this cell, why am I having 13 cells in series and 10 cells in parallel configuration. So you should know this information. That's why uh, that's what we stress here. Okay. Okay. So now, okay, now the parameters to be considered for the cell selections. It's pretty same, or maybe we looked at the same information for a motor. So we should know the nominal voltage of the cell, the cutoff voltage, capacity, specific energy, energy density, continuous discharge current, internal resistance as well, and you should also know the C rate of your C rate of the battery and the cell. So cutoff voltage is when I mean at certain, I mean, to protect the system from under voltage, you should, I mean, when you have a motor controller and a battery managed a motor controller rated at, to operate between certain voltages. So when you reach this cutoff voltage, your battery should stop providing power to protect the other systems present. You have your DC and so on. So this is why we have this cutoff voltage on the lower limit and the upper limit, and capacity. So these are the parameters that you should consider for while choosing a battery pack based on the calculation. So when we take now, maybe if we want to take quickly brush up on all the topic we discussed from the beginning, we looked at or we understood what are the forces that contributes for propelling the vehicle, and from the forces we calculated the torque, and then we calculated the power. From the power, we understood that, or we understood that this is the rating or the power rating that I should have for my motor. And with that, we chose the motor controller. And when we know that my motor should get 2 kilowatt of energy, now we are choosing a battery pack which should be capable of providing the energy demand of the motor. So this is how we do a selection of components, especially for now, at least in this case, selection of your motor and the motor control. I mean, battery and the motor. Now, now let's look at some interesting topic. Drive cycles. Have you heard of this drive cycles? Because slightly different. I mean, that's specific for the battery. I mean, to make it simple. So drive cycle. I mean, we are having a, let's say we buy a bike or a car. Now we are not going to or like we saw, we are not going to always have resistance force, linear acceleration, linear force and angular forces, right? So we follow, or let's say we start from, let's say, place A to B. We'll be braking, there'll be pothole in the road, we'll be braking, then there'll be uh, uh, a nice 100-meter stretch where we'll be cruising at higher speeds. Then there'll be a maybe probably a traffic signal and so on. So the way we are going to drive is not always going to be the same, right? So we are going to be in a cycle. So for how do we how is a vehicle certified to be driven on the road, or how do they test the vehicle? So this is done, or maybe they're replicating some sort of cycles to do testing a vehicle. So this is, I mean, drive cycle in short is a plot of velocity versus time. It's just a plot of velocity versus time. And let's say if your vehicle has to be certified in this drive cycle, say EUDC, now your vehicle has to be driven in this pattern, meaning at 0 seconds, or let's say between 0 and 200, say I'm assuming say 10 seconds, I should reach 20 or 18 kmph, and then I should gradually come it down, reach 0, and then I reach 35 kmph, and so on. So this is a drive cycle. It's a plot of velocity versus time. So for a vehicle to be certified, I mean, there are, I mean, different countries, different regulations follow different drive cycles. But this is one example, or just to give you an idea of drive cycle. Why am I stating this point here? So why in simulation tools that are used? Now I'll quickly show you maybe overview on maybe one of the simulation tool. I mean, this is not to tell you to use or asking you to use the simulation tool, but I'm going to show you the parameters and the inputs that are given to this, which is similar to whatever the parameters input that we chose. But using the simulation tool, we can capture the dynamics. When we wanted to do a range calculation for a specific driving cycle, or for a path, let's say I want to travel from, let's say, Chennai to Trichy, or I want to travel from maybe from Delhi to Gurgaon. Now, what I do, I have map, I have elevation, I have all these data. Now, if I want to do a realistic comparison, I can use simulation tools like this. Or in other words, when I want to do before I develop a vehicle, I want to choose the component carefully, choose the motor, battery. We can take help of this simulation tools to perform this. So here for this example, I'm just sharing the MATLAB model that, or there is a toolbox, vehicle composer, virtual vehicle composer is a toolbox present in MATLAB. Here, all this, I mean, we have building block. I mean, these are blocks that are already present. Now I can choose. I mean, it's like plug and play. But uh, let's look at what I want to tell you here is to look at the data that are going inside this simulation. Okay, so first I had this configuration where I selected a single electric vehicle with one electric machine, and then I chose, at least for this, I chose the Simulink template. And for the vehicle dynamics, at least for now, I'm interested in the longitudinal dynamics. I'm not interested in the lateral combined longitudinal and lateral dynamics. So okay, something happened. Okay, I'm going back. Okay, and what are the data and calibration going inside? So there are different, again, different blocks. When I look at the chassis, okay, pass car. There are some ambient informations that are requested. Okay, pass car. So vehicle mass. We, for our calculations, we use mass. So we are asking, I mean, mass, vehicle data, longitudinal distance between the center of mass to the front axle, uh, velocity, um, and then longitudinal drag area, drag coefficient, and then some of the chassis parameters like the vehicle mass. Okay, we just saw this. Yeah. Okay, and then tire data. So simulation, in short, simulations are like, I mean, the more we provide the data, uh, uh, the more accurate the simulation results would be. So these models have pre-filled data. Now we have to make sure, if in case we are using these simulation models to estimate the energy consumption or doing a full load calculation. So you have to ensure that the data that is present is relevant to what we are interested for the vehicle. Okay, brake control unit, type of controllers. Even I'm experimenting this for the first time. Just I thought I had this MATLAB model, so I was trying to open to show you this. And electrical systems, you have DC-DC converters. What is the power limit of the converter, efficiency of your DC-DC converters, and losses. Electrical machine, the graph, I mean the torque value, the plot of the electrical machine. Let's say for this, at least this model, they've chosen the machine with uh, torque of maybe plot which has the speed up to, let's say, 600 or yeah, 500 uh, up to 500. You have a torque of constant torque of 450 Newton meter. So, so these are pre-filled data that is present, and the energy storage device. What is the rated capacity at nominal temperature, initial battery capacity, number of cells in series, number of cells in parallel, OCV, open circuit voltage of all the cells that is present in the battery pack, internal resistance, breakpoints, and so on. And for the driver and environment, drag coefficient, rolling resistance coefficient. For the environment, what is the atmospheric pressure, ambient air temperature, and so on. Scenario testing, here is where, I mean, if we are looking at some legislative cycles, we look at FTP. I mean, we have different drive cycles. Uh, we have Indian drive cycle, MIDC, modified Indian drive cycle, according to what the legislation or the country that we want to mimic for the testing. We can use this data as well, which is in short a velocity versus time plot. You can also have your own test data if you are going to test your vehicle in your college campus and you want to simulate something. You can even record the data versus time, velocity versus time, and you can also have it's just an Excel plot. And what are the information that I would like to see? I can specify it here. Now I have the vehicle model built. I have the vehicle model built. Since this is in Simulink, I can go inside and can check how the plant model is built. When you look at the controllers, we have brake control unit, BMS, and BMS sensor sensing, and so on. These are pre-built model. Okay, and when I simulate, when I run the simulations for let's say FTP, or I don't see MIDC here, but if I were to run that, I can see how the battery voltage. Let's say these, I'm calculating the dynamics now. You see, over this drive cycle of, let's say, 204 2400 seconds, this is how my voltage, battery voltage is getting reduced from 364 to say 360.5. And I have my electric machine speed, e-motor speed for this drive cycle from yeah, over the time it's rising from, let's say, 0 RPM to 260 RPM, and so on. And this is my torque. Uh, and acceleration feedback, battery current. This is how my current has been discharged. Now if I were to do the energy consumption calculation, I could easily study now that when I integrate all the energy consumption over the time, now I'll get the total amount of energy consumed for me to drive 2400 seconds for this drive cycle. So the dynamics of the calculation that we did, if you get chance, I suggest you to use any simulation tool, or there are Excel uh, templates also available in the internet, so you can use that to do this dynamics calculation as well. Yeah, so this is quickly about simulation. Now maybe some other general informations, or maybe information, the IP rating. Okay, display. The I mean, most of us are pretty familiar, but please also check the IP ratings before you buy or source your batteries and motors. And if you want to decode this information, the first digit represents the solid and second digit represents the liquid protection. And here is it. If you are IP00 rated, that means there is no solid and moisture protection. If you are IP66 protected, you have totally protected against dust, both, yeah, dust and also the moisture. There are also further or maybe standards IP 5K, 6K, and so on. So while you read the data sheet, also take a look on this consideration as well. Well, Hannes, I want to also mention this point. Mandatory connector between the battery and load. For the final competition, we'll be using an energy meter to record your energy consumption data for the range calculation or the durability energy consumption calculation. For that, what we suggest is to mandatorily have an Anderson connector uh, coming out of your battery pack, and with this Anderson connector, that's how your energy, your wiring harness should be from the battery to fuse and then to the load. So you can be flexible on the right side of the schematics, but we want to have an Anderson connector between the battery and the load just immediately after the battery. Okay. And yeah, some of the, I couldn't list all. I was preparing in a hurry for this presentation, but take a moment to look at all the automotive or the global standards that are present. While if in case you are not clear how should I choose this parameter, take a moment, look at the standard to get this information rather than assuming or looking at some general data available in the internet. Okay, and these are reference that is used for in this presentation. Okay, and I also referred these websites and links for preparing this presentation. It's long, but yeah. So this is all I have got for today. So I'll give you some idea about all these components in the rule book. Okay, so maybe these are more self-explanatory, but we'll give you some. I'll use this few minutes of time to brief you on that. So, the whole competition is divided into four phases: design review 1, 2, 3, and 4. Why this is done in any automotive company or any product development company? The development is split into different phases, wherein the first phase should be most on the design or initial analysis, design and cost estimation and things like that. And design, the second gate, we call it gates at few organizations. Second gate would be like around the manufacturing, about the manufacturing, uh, the manufacturability, and so on. And then would be your static evaluations, and then the dynamic evaluations. That's how it is also structured here. So we have this event divided into four design reviews. So what do we, I don't know if there are also participants who are part of other SAEISS, maybe electric two-wheeler competition or the previous year's electric four-wheeler, but we have split into four phases. The first phase would be where we want the participants to submit the master layout and the design report. Master layout of the whole vehicle, and the design report of the components that is specified in the rule book, and that was also discussed during the CAD modeling trainings. So critical dimension calculations and the powertrain simulations, this would be your calculation of your what should be the size of your size of the tube that you are going to use for the frame, why do you choose this material, and so on. And then the powertrain calculations, all what we saw today. What we saw today is maybe an overview of all the formulas and so on. But we would like to or spend some time. This is not. Think one thing I would like to stress here is this is not anything for this competition. Rather, take this opportunity to understand how these parameters are considered, and how frontal area is going to play a vital role in your coefficient of, your aerodynamic forces, or how your mass of the vehicle is going to impact hugely on all the forces that you have to overcome. So take this seriously, do a powertrain calculations, also the This should be submitted with in the DR1 report. And simulations. Try to use simulations also possibly for estimating the uh, 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 yeah, for selection, component selection. You can use uh, take this opportunity to use simulations to select the components. We have we have selected one point, and then we calculated what is the total power required. But you can also use simulations to understand realistically what would be the power that is required. Do a comparison, take a motor of rating, I mean, X kilowatt, and then do a simulation and see how much energy you are consuming, and try get a different motor data, feed in the data to the simulation tool, and see how the change in parameters are affecting, or how much energy you are additionally consuming, or how much energy you could save using this motor. And then CAE reports, CAE report of your chassis, and then there I saw that components listed here, which you have to submit the CAE reports. Use the CAE simulation tool, uh, which is in your I mean, which is available at your laboratory and so on. But what do we want to see here again? We don't want to see, or maybe the whole point again here is get an experience doing a simulation, and understand what is the information that you are feeding. Let's say you're applying a load of X kilonewton at a joint. Now understand, see how it is affecting, how, what is the deflection, what is the stress that you're getting. And there are simulation tools that doesn't tell you that your member is going to fail. So you are the one who should know that what is the Young's modulus of that component, of that member. And if this is the stress that is acting on it, it probably is going to be a catastrophic failure. So do it, and also understand how to read that data that is given, coming out from the simulation. And the report, ideally, it should not be just the images of a colorful plot. Rather, it should be a summary of what is your interference from that simulation. Or if you have done the first iteration and there is a member that is weak, please also record that, and then also specify this is the updated design based on the finding from your simulation. So that way it would be helpful for you, and we would be happy to see that, or we'll be happy to know that you have learned something. That's the whole idea. And part drawing after CAE, this is very specifically written after CAE, for the fact that we assume that you had a design report or design made, and then when you did a simulation you found out that, or it can be many cases that uh, the results from the CAE has some impact, or should have given you an idea that this design is not can be improved, and you went for a second iteration to modify your design. And that's where we want to have the part drawing after the CAE. And E-bomb. So list down I mean, all the bill of materials, your bill of materials for your vehicle, detailed bill of materials. And then cost estimation should not be just the components that you're buying. This would be the cost estimation for you to build this vehicle, meaning there will be cost for manufacturing. You'll have service cost for bending a member, and then for welding and so on. So take the lead time taken for all these. So do an effective analysis on this manufacturing drawing. So what is the difference between your just a CAD design report and a manufacturing drawing? Anyone? So you have designed a CAD model of a component. You're going to give it, just you're printing it, and you're giving it to a manufacturer. Will he be able to manufacture it?
We have to add a geometric tolerance and dimension. There's an
Correct.
extra.
So there are detailed information that are required for manufacturing. The tolerances, surface finish. Uh, so so manufacturing drawing for the components that you have designed for your vehicle should be having all the informations. And then one point, I would like to also mention is that the design report that you submit, we all have come across engineering drawing. So we have a format to report. So please use that template. Mention the projection and mention the part number, part name, the unit very specifically. Many of the times we have seen that the units were not mentioned. So these are information required. So we're not just doing an activity, but this is going to be a learning and an exercise. So let's try to be as serious as possible. And then inspection report. So in this inspection report would be ideally, how are you going to inspect? Say, how are you going to inspect a building? How are you going to inspect the uh, uh, a member? So those information are required in the inspection report. I'm also not very familiar on that. There is a table provided, but if you have questions, reach out to us. And then okay, so then comes the DR3, which are your the static analysis. So static analysis of the stability of the vehicle. We look at the suspension, I think. Yeah. Aesthetics of the vehicle, the weight would be calculated, weight would be measured, the build quality, and the innovation assemblage, these would be analyzed. Probably as a part of DR2, you may also have to submit the or DR2, or just after the DR2, you may have to submit the videos of assemblies. Probably you will get the email or communication on when you have to submit this information. But then for the final competition, it would be your design log presentation, your design, why you chose that design, what is unique about your design, and so on. And then the dynamic test, like the maneuverability, vehicle range, acceleration, braking, and gradability. So we'll have specific tracks for maneuverability, for acceleration, braking, gradability, and bump tests. We'll have specific tracks for the vehicle range test. Uh, this is where the electrical layout that I was presenting in one of the slide, where an Anderson connector is required between the battery pack and the load is needed, where energy meter which should be connected between the uh, yeah, which should be connected between the battery and the load, and the energy consumed by your vehicle for driving a set distance, or maybe to cover a track, would be calculated. And the one with the very least energy consumption, who's more efficient, would be awarded accordingly. So in short, this covers the whole cycle of the development in a company, in an organization. So this is quickly what I would like to cover. I see.